Hello and welcome to the AICE Chemistry lecture series. In this video, we're going to look at chapter 18, section 3, which is going to introduce us to the first reaction of aldehydes and ketones. And that is going to be the reduction of aldehydes and ketones. This is actually the opposite reaction for the reactions to create aldehydes and ketones that we saw in section 2 of chapter 18. In section 2, we saw the oxidation of primary alcohols into aldehydes and secondary alcohols into ketones. Well, we can reverse that process and turn aldehydes into primary alcohols and ketones into secondary alcohols through reduction. So let's look at what that is going to look like. In the case of aldehydes, they can be reduced into primary alcohols. So we can grab an aldehyde, and we actually have two different reactants that we can use for this. We can react an aldehyde with any of two very common reducing agents. The first is going to be an alkaline solution of sodium tetrahydroborate. So the tetrasodium hydroborate, which is NaBH4, is a very common reducing agent that we do use to reduce organic compounds into a bunch of different things depending on what organic compound we're starting with. In the case of aldehydes, if we use NaBH4 that is aqueous, so in water, and alkaline, meaning that we have some form of base in here, so this alkaline is usually going to be NaOH, although it could also be KOH. So NaOH or KOH. So if we use alkaline sodium tetrahydroborate, NaBH4, in water, and we heat it up or we warm it with our aldehyde, we are going to get a solution of primary alcohols out of it. So warming would be a condition here. So warming is our condition, and our reactants would be aldehydes with alkaline aqueous sodium tetrahydroborate, NaBH4. So what that reaction will essentially look like is that if we have an aldehyde like this one, the part we're going to be focusing on is our carbonyl group, because that carbonyl group, upon reduction, remember, for reduction we use H in brackets instead of the actual reactant. So we wouldn't put NaBH4 here, we'll just put H's in brackets. What's going to happen is that that carbonyl group will have hydrogens added to it and turn into a alcohol. Now you have to be careful here. It's actually two hydrogens that get added here, because there's one hydrogen that is very clearly visible that we add to the oxygen when we break the double bond. But there's another hydrogen that we might not be thinking about here. So we break this double bond, we break the pi bond of the double bond, we add a hydrogen to the oxygen, but because we're breaking the pi bond, this carbon right here also gets a hydrogen added to it. That's where the two comes from. One hydrogen for the oxygen, one hydrogen for the carbon that was double bonded to that oxygen. So that's a reaction that happens anytime an aldehyde gets reduced. Well, we have another alternative reactant that we can do this with, and that is going to be lithium tetrahydridoaluminate, LiAlH4. So very similar, along the same lines here, but with LiAlH4, when we add our reactant, when we add that LiAlH4, oops, I'm going to put in yellow because it is a reactant, it does have to be in dry ether, not in aqueous solutions. Now this is something that we saw before. We saw this earlier when we were doing other reduction reactions. LiAlH4 has to be in dry ether because it will react with water. So this reaction, even though it does not require warming, there's no special conditions, it does require the LiAlH4 to be in dry ether. Now, I do want to make very clear something. This is an either or, not a both. So we can do the reaction with the NaBH4 in an alkaline aqueous solution with warming, or we can do it with LiAlH4 in dry ether. It's not both of them. There's not sequential reactions. We simply have two options. It's an or. And in both scenarios, the product we would get out of this is going to be a primary alcohol. Because the carbonyl group on product. So because the carbonyl group on an aldehyde is in the terminal carbon at the end, when it gets turned into an alcohol, that alcohol is going to be on the terminal carbon, meaning that we will get a primary alcohol out of this reaction. Now, the reaction, the reduction of ketones is very similar. So again, ketones can also be reduced with the exact two reactants we just saw. So the reaction with ketones for reduction is exactly the same as the reaction for aldehydes. We use aqueous alkaline sodium tetrahydridoborate, NaBH4, which needs to be aqueous, it needs to be an alkaline, and it needs to have warming as our condition, so it needs to be warm for the reaction to happen. That is one option here. And the other option is the exact same other option we had with aldehydes. It's going to be lithium tetrahydridoaluminate in dry ether because, again, that LiAlH4 reacts with water. So the exact same reactant we use for the aldehyde, we can use to reduce the ketone. Because, again, these two are the most common reducing agents there are in chemistry. So the only difference is that because in a ketone, the carbonyl group is on a middle carbon in the chain, when that double bonded carbon-oxygen bond is broken and hydrogen is added to the oxygen and to the carbon, because remember there's a hydrogen being added here, that's where the 2 comes from, we'll get the hydroxyl group, the alcohol group, in the middle of the chain, giving us a secondary alcohol as a product. So the only difference between the reduction of a ketone and the reduction of an aldehyde is not the reactants, it's the products. We will get a secondary alcohol with a ketone and a primary alcohol with our aldehyde. And that's because, again, these two are extremely common reducing agents. Now we learned all of them. So something to keep in mind here is that anytime we see either of these two reactants, NaBH4 or LiAlH4 in dry ether, that means that the reaction we're undergoing, it's a reduction. That happens every time. So if you see these, you know it's a reduction reaction if you're asked what type of reaction is this. Similarly, for oxidation, let me make that a little more round. For oxidation, the two types of reactants that will always tell you have an oxidation are KMnO4, potassium permanganate, and K2Cr2O7, potassium dichromate. You see these two, you know you have oxidation. So keep that in mind. Anytime you see these two, or anytime you're asked how will you reduce this compound, these are your two choices. Anytime you're asked how will you oxidize this compound, these are your two choices. So those are the reductions of aldehydes and ketones. Like I mentioned, these are the opposite of the oxidations we saw in section 2. So it stands to reason that if oxidizing a secondary alcohol gives you a ketone, then reducing a ketone gives you a secondary alcohol. It also stands to reason that if we oxidize a primary alcohol, we get an aldehyde. Then reducing a primary alcohol will give you reducing an aldehyde will give you a primary alcohol. So keep that in mind. A lot of these reactions, even though we see them as separate reactions, we see these as two separate reactions, we see the reduction, the oxidation reactions as separate reactions, they're really just opposite sides of a coin, opposite sides of the reaction. Don't memorize this as 4 different reactions. Memorize it as primary alcohols can be turned into aldehydes through oxidation. And so the opposite process of turning aldehydes into primary alcohols will be reduction, because reduction and oxidation are opposites. Secondary alcohols can be turned into ketones through oxidation. Ketones can be turned into secondary alcohols through reduction. And then remember that there is no special circumstances here as far as the oxidation and the reduction. Oxidation gets carried out with either KMnO4 or K2Cr2O7. Reduction gets carried out with LiAlH4 in dry ether, or with NaBH4 aqueous with an alkali. And this works for both of them. That reduction arrow in the bottom, for either of them, we can do it with either of these. That oxidation arrow at the top, for either primary or secondary alcohols, we can do with this. And even the observations are going to be consistent. Dichromate, K2Cr2O7, goes from orange to green, regardless of when you use it. This is always going to turn from orange to green, regardless of whether it's used with a primary alcohol, a secondary alcohol, or any other oxidation we have seen throughout this year. Potassium permanganate is going to go from purple to clear, regardless of where it's used. As long as it reacts, it's going to turn from purple to clear. So don't try to compartmentalize these reactions. Learn the reasons behind the color change. Learn the reasons behind why we choose these reactants, because they're oxidizing agents. The reason why we choose these products, or these reactants, because they're reducing agents. And that will make your learning of organic chemistry a lot easier. And that's it. That's it for section 3. It's just another reaction. It's just the opposite reaction we saw in section 2. I will see you all in the next video to start discussing some other types of reactions that ketones and aldehydes can undergo.